for the next talk. So the way we organize the workshop, we have experimental and theory sessions every day. And today we start with the session that is devoted to experimental concepts that operate below the megahertz. And the first speaker that we have is George Winstone. Please, George, start sharing your screen. George is based at Northwestern University, and he will tell us about levitated sensors. So the talk is 25 minutes plus 5 minutes for questions, and I will give you a reminder, a 5 minutes reminder. So the floor is yours.
Thank you very much. Can I be heard well? Can everyone hear me?
I think it's fine, yeah.
Wonderful. Okay, great. Thank you for introducing me. So just a quick note to say that it is very early here in Chicago, so please give me some allowances. Okay, well, thank you for the great introductory talk. I thought that set the stage really well. Yes, my name is George Winstone. I work in the Geraci group at Northwestern University. And I'm here today to talk to you about detecting high-frequency gravitational waves with optically levitated nanoparticles. So this is a collaboration between the Center for Fundamental Physics and Sierra, which is the Center for Interdisciplinary Research and Exploration in Astrophysics. So in layman's terms, it's a collaboration between the experimental tabletop guys and the real astronomers, which I think is very positive because that's where the exciting stuff tends to happen. So a little bit about, hang on. There we go. A little bit about the structure of this talk. Since this is aimed at quite a wide audience and there's a lot of people attending, I'm going to give a bit of an introduction to levitated optomechanics first, or a refresher, if you will, and then going to sort of place our experiment in the context of the gravitational wave sources we'd like to look at. And then I'm going to sort of combine the two concepts and sort of sell you on the idea that we can use levitated optomechanics to detect gravitational waves. And then I'm going to spend some time talking about the sort of technical challenges we've encountered thus far and the ones that we think we'll encounter in the future and how we might overcome them. So I'm sorry for subjecting some of you to this joke several times in a row, but of course this conference is online and these are unprecedented times, but I thought it was quite funny that the use of the word unprecedented is in fact unprecedented in and of itself. So yes, levitated optomechanics. So what we do in Andy's lab and what I did during my PhD and what many people in this field do is we trap polarizable neutral glass particles at the focus of a high intensity laser beam. And by glass, I mean silicon dioxide typically. And then when this trapped particle is a sphere, the degrees of freedom, the motional degrees of freedom tend to be decoupled and you end up with 3 decoupled classic harmonic oscillators. You can then eat away at kind of the classical sources of noise in that system by various feedback techniques. And then you'll end up with 3 decoupled quantum harmonic oscillators in principle. And this was very recently done for at least 1 degree of freedom. So to give you an idea about the characteristic sort of size scale here, these spheres or other shaped objects that we're trapping tend to be tens of nanometers to a small number of tens of microns. And then sort of at the lower end of that scale, when you have something 60 nanometers or so in radius, that's about 1 billion atoms that you're trapping. So why are these objects useful? Well, they have an enormously high Q factor. The theoretical Q factor for these systems is up there in 10 to the 12. The force sensitivity demonstrated so far is pretty good. I'll talk about that later. And you can also trap across sort of quite a wide regime of physics, which is interesting. So I've got a diagram here on the bottom right-hand side of something trapped in the Rayleigh sort of limit and then the ray optics limit. And then we're kind of in between those two regimes at an interesting point. Of course, ground state was recently achieved in this field, which I'll mention later, but that's quite exciting because, you know, when you have something 1 billion atoms in its quantum mechanical ground state, that really starts to challenge the limit of quantum mechanics. But in this case, I'm just talking about these systems in terms of force sensitivity. So to give you an idea about what sort of this abstract canonical diagram on the right-hand side looks like, this is real photos from my lab. So the left-hand side top down, that's the visible light photo of what's going on in my experiment right now. Right-hand side is an infrared camera view of the same thing. And then this is one of these particles trapped at the foci of these 2 optical couplers. So on the last slide, when I draw you this sort of diagram, this potential well with the test mass sitting in, this is the test mass that I mean. And then each of these degrees of freedom forms a nice Lorentzian in the frequency domain. And then that's kind of how we tend to read out our system. So, I mentioned that this field recently saw ground state recently, and, kudos to Marcus and Lucas for achieving that. And this is interesting for two reasons. First, it shows that these systems are enormously sensitive in terms of their readout capability, and B, that there is a lot of technological development in this area. It's a very rapidly moving field. So I want to use these trapped microspheres to be a force sensor. What are my fundamental limitations? Well, the first limitation you tend to run into is the background gas in your vacuum system, right? So the picture I showed you, I had a glass microsphere trapped at a laser beam. I have to pump all of the gas out of my vacuum chamber. That's my primary noise source. Random kicks from the particle interacting. The particle has a finite temperature. It has an external and an internal temperature, which can be assigned, kind of the surface temperature of the atoms versus the center of mass motional temperature. It's that center of mass motional temperature that we consider in terms of feedback and force readout. But when I've pumped all the gas out of my vacuum chamber, I'm still limited by the next biggest source of noise. So this data on the right-hand side, this was taken by Lucas Novotny's group a couple of years ago, and it's really nice because it shows you the kind of once you get rid of one noise source, you then have to deal with another and then another. So this right-hand side graph down here, they're taking all of the steady state temperature of their particles being reduced as they suck all of the gas out of the vacuum system. And then once they've done that, they reach this photon recoil limit. So what is photon recoil? That is the probabilistic interaction of photons with your object being scattered in a semi-random direction away from it. It's in the limit of a small particle, it's the Rayleigh scatter. And then in the limit of a large particle, it's the Mie scatter. And this is interesting for two reasons. First, in terms of your temperature is given by the ratio of your heating and cooling terms. But what we really care about here is force detection. And when you're trying to measure a small force, you're basically limited by the largest source of random numbers in your system. And once I've gotten rid of all the background gas in my system, I'm then limited by the random interactions of photons with the mechanical oscillator. That's the point here. So this limits the best force you can measure with these systems. And the key takeaway that I want to give you here is that this photon recoil process is heavily dependent on the geometry and size of the particle. So when it's very small, I'm looking at Rayleigh scattering. When it's much bigger, I'm looking at Mie scattering. And then, if I want to compute the sort of total dynamics of things, including the shape, I'm looking at Mie-Lorentz theory, or numerical methods. But the point here is when I make my particle bigger and I make it flatter, then more of the photons go forward and backwards respectively, and this will be quite important later. So this limits your force, but what can you really do in terms of force? So this is a piece of work done in Andy's group, the group I currently work in, a couple of years ago before I joined, where they demonstrate Zepton-Newton force sensitivity. Zepton-Newton, the suffix is 10 to the power of minus 21 newtons. So that's a very good measurement. So to give you an idea, the integration time on this graph on the right-hand side, that's about a day, or maybe just short of a day, 10 to the minus 21 newtons. And then you can think about these forces in terms of, you can think about these sensitivities in terms of forces, acceleration, or displacement. And then if you look to other sort of parts of the community of, do you want to measure in newtons acceleration, displacement, you can look at some work done by David Moore, where they, I think, showed, 10 to the minus 5 G sensitivity on acceleration, and then some picometer displacement sensitivity by Marcus Asperger quite recently. So these systems are very sensitive. These objects are very good sensors. So now that we know it's a good sensor, what do we want to use it for? Right, so gravitational waves discovered recently by LIGO in 2015, although 2015 is pushing the definition of the word recently. I'm sure everyone's familiar with these graphs at this point from the Livingston and Hanford detectors. So the point is, as the previous speaker was pointing out, well, I mean, LIGO sees one part of the frequency band, and what can we do in other parts? So this graph was actually made by, I think, the university's marketing department to sell the idea that, we're in a different frequency band. And then, of course, in this conference, we're actually at the lower end of this stuff. So I guess that's a little unusual for me. But the point is that LIGO and Virgo, well, of course, they're on the kilometer scale, and they capture certain parts of astrophysics. They capture certain physical processes, and they look at certain objects in the sky. And then LISA, the upcoming European Space Agency L-class mission, it's on the megameter scale, and it sees different processes again, different parts of the sky. And then this is a picture of our lab on a fairly typical day, and it's down there on the meter scale. And then we're looking up here at kilohertz processes. And then, of course, you talk to different parts of astrophysics at that point. So LIGO and Virgo, this is all fairly sort of standard model of astronomy stuff. And then up here, the things that we want to look at, well, it's a little bit different. So the two things we're looking at here are axions, that's specifically the QCD axion, and primordial black holes, and the interaction of those two, perhaps. So this is what we want to look at. How are we going to look at it? The configuration of our sensor is a microscale interferometer, much like LIGO, but it's a resonant sensor at the same time. So it's rather like those very old resonant bar experiments, except that the resonant bar is levitated with the high Q factors that I mentioned before. So these are our two levitated objects in two cavities. And what my gravitational wave does is it comes in and it transduces it starts a change in proper length in my cavity. And the key thing here is that this is free floating, this nanoparticle. So the change in proper length from the input mirror to the nanoparticle changes differently to the proper length between the start and the end of the cavity. So what that process does is it transduces a change in proper length into a force on the particle. As I showed a couple of slides ago, these particles are enormously sensitive force detectors. So, okay, how good can you really do with these things if that's the basic principle? So this is from Andy's original paper back in, I think, 2011. And then you can easily ask the question, okay, well, if you have only $1 million in a tabletop, how can you reasonably expect to compete with LIGO, which has much more than that and occupies much more space? And the point is it doesn't compete directly, it's in a different frequency band. So this red banded curve, that's LIGO's sensitivity. And then up here, way beyond the free spectral range of LIGO's cavity is where we are sensitive. So these dotted and dashed lines represent different configurations of our system. So there's two things I'd like to point out on this graph. The first is that it only really dips better than the LIGO sensitivity above this 10 to the 5 Hertz point. The second is that this configuration where it's written sphere here, that means we're trapping spheres in the optical trap. And these other configurations, we're trapping disks, flat-faced disks. And that's from that photon recoil effect I mentioned at the beginning of the talk. So when your object is flat-faced and large and to a good approximation flat from the point of the optical mode in the system, most of your light scatter from your Lorentz-Meyer interaction goes forwards and backwards from your flat-faced sort of to the beam object. Whereas when you have a sphere, even a large sphere, the mode of the light that's scattered from it is sort of incompatible with the light in your cavity. So it's a very lossy process. Right, and if you can recapture a lot of these scattered photons in the same optical mode as your trapping mode, then that noise source is sort of substantially suppressed. So that's why these lines are so much lower than this line. So what that really means is that we have to trap these flat-faced objects to make this system work. The second thing, reason for why you can really compete with LIGO is the different scaling of the noise sources, again, in the frequency band way above its free spectral range where it's designed to work. So LIGO is laser short noise limited, whereas our system is Brownian thermal noise limited, and the frequency scaling of those two processes is very different. So that's the kind of the canonical picture I showed you a couple of slides ago. What are we really building in the lab? Top of the right-hand side here, this is a CAD diagram of the parts we've kind of designed and ordered. This is what's... Are you guys seeing a picture on this slide?
No, it's white.
No.
Oh, there we go. Okay, hang on, I've gone out of share mode and it started working. There we go, great. This is what's going on in the lab at the moment. This is all the hardware that's sort of arrived so far. We're putting this together. We're sort of playing the same game everyone else is during the pandemic, which is waiting on very long lead times for parts. So construction of this is very much ongoing, and we hope to have some updates soon. I'll just jump back to full screen mode for the rest of the slides. Great. So what are we doing while we're sort of constructing this? Well, at the same time, we're trying to optimize kind of the design of the system as we're putting it together. So there's a fairly recent paper on the archive by us where we're optimizing the levitated objects. So I kind of gave an impression earlier that we have to use disks rather than disks rather than spheres, and that's true. But we actually think we can do a little bit better than disks as well. So by disks, I mean very thin disks that are very sort of wide in this axis and thin in this axis. And what we'd like to do is we'd like to swap those out for stacks, optical stacks of different refractive indices. So on the left-hand side here is one of the disks that we fabricated in a clean room. That's a picture of a disk on a bit of clean room towel. And then this is a finite element model of one of the stacks that we're talking about in our recent paper. So what we'd like to do is construct something that's alternating between silicon and silicon dioxide, and then we match the length, the wavelength of the light in our cavity. And the purpose of that is basically to get the mass in our system up to increase kind of the range and sensitivity of the instrument, to strain. And the reason for that is actually from these equations back here, in that your sensitivity to strain scales with your mass. So the bigger you make, because it's a general relativity sort of interaction, so the bigger you make your levitated object, the better you do, with the caveats that you can't crash your mechanical frequency or your Q factor, and it can't melt in the laser beam, obviously. But we think we can meet all of these design constraints, and that's what we've sort of talked about heavily in our recent paper, of why we think we can optimize this levitated object a little bit more. Key things to take away from that paper is to keep the sort of finesse of the system high enough, these objects really do have to be flat-faced, which means they actually have to be a little bit bigger than the mode that we're trapping them in. So how much better does that really give you? Well, again, the scaling is pretty linear with mass. So this is a comparison from our old book, Andy's old paper from 2011, and the paper we put out recently. And this is really at the point where we think we can get into regimes of novel physics in terms of sensitivity. So that's exciting. Sort of required challenges before this really goes online. We started building this 1 meter prototype at Northwestern. There's a couple of directions we want to improve the levitated object in. We'd like to build these stacks, and we want to make sure they don't melt because they're pretty big and they're going to get pretty warm. I showed you pictures of disks on clean room towers, and I've showed you pictures of spheres in the optical trap. That's because we haven't quite got a disk into the optical trap yet. We are working very hard on making that the case. And then when we trap the disk, we'd like to demonstrate that its photon recoil number is really low enough to give you the sort of sensitivity increase that I promised earlier. We'd like to be able to load our objects in high vacuum. LIGO and related detectors, they have quite a high duty cycle during their observation runs. As I think anyone in the field of levitated optomechanics would tell you, a duty cycle of 80% is above what these experiments do presently. And then we really need to learn how to do the signal readout from 2 nanoparticles trapped in both arms of the microscopic interferometer at the same time. This, I guess, is done fairly often in LIGO, but for our system, it's going to be a little more complicated because you also have the scattered field from the object inside the cavity. So the mode that's sort of recombinated at the beam splitter is a little bit different. So we might have to be a bit clever about that. And then obviously the last challenge is the current phenomenological climate in the United States. So this is just a fun little factoid. I had to sue the State Department to get through the border this year. And please ask me about that later if you're interested. It's a fun story. Right, so yeah, a little bit more in detail about those technical challenges I mentioned. So disk fabrication, we're using a top-down process to build our sort of bespoke levitated oscillators. And the reason for that really is the water content. So these nanoparticles, the spherical ones, they're made from bottom-up processes like the Stober process. And that tends to leave you with a lot of water in the system. And building them top-down, we think we can do a lot better. Left-hand side, that's a top-down groove of lithography sort of on the substrate. Right-hand side, that's a clean room towel again. You know, how do we really load these things into the trap? So this is a glass slide above the picture of the experiment I showed you. This white powder you see here, that's a, I guess sort of like a dried solution of these particles sort of on a microscope slide. Inside this, underneath this ceramic plate you see here, there's a PZT ring. And what happens is we drive a very high voltage through that ring and it literally throws the nanoparticles off the slide into the optical trap. So bottom right-hand side here, this is a GIF on my slide here. And if you squint a little bit and the bandwidth is good enough, you should be able to see there's like a snow of nanoparticles being fired off the bottom of our camera. So you get quite a lot per launch. I thought that was a cool picture to take. But there is a real scientific value in capturing these things at lower pressure. And that's because of the high sort of experimental cycle I mentioned that we want to get earlier. So during my PhD, at least, we'll be using nebulizers to trap these things, which means you have to open your vacuum chamber, trap, and then pump down your vacuum. And then when you lose the particle, you have to do that process again. And we can trap these things at vacuum, but not high vacuum. And then, of course, turbo pumps take a finite amount of time to spin up and down. So we'd like to be able to run these things really at UHV rather than just V. And what are the issues with that? Well, when you trap things at vacuum, you still have a viscous drag force from the residual gas inside the chamber. And then when you're at UHV, you don't have that anymore. And what we've been trying to do is replace it with an optical drag force. So here's a video of particles passing through our trapping region without a slowing beam engaged. And this is with a slowing beam engaged, and the velocity is lower. So this is something that really works in principle. And what we're working on is kind of the engineering side of a lot of these problems to make the instrument sort of reliable, to make this sort of system reliable. Okay, yeah, so in summary, yeah, we've begun construction of this 1 meter prototype. I promised the theorists that we would have some data before Christmas. I really hope I can keep that promise, but we'll see how things go. There's a lot of these enabling technologies like sort of increasing our trapping efficiency that's happening in parallel. And optimizing our levitated objects. There's a paper we put out very recently that's in review at PRL at the moment. This is the timeline that Andy gave me very kindly the other day, assuming no more global issues crop up in the near future. So we're still very much in the stages of putting the interferometer together. But what I really hope to be able to do soon is trap some things in it and characterize the noise. So when we presented to the gravitational wave community in the past, we always get asked for a noise curve, right? Which is incredibly reasonable as a thing to ask. And I hope we can provide one soon. And then kind of in concert with those things, we've been developing stuff like data pipelines for the theorists and so forth. So in terms of upcoming papers that we hope to put out in the next 2 years, and therefore stuff that you guys can read, this is about optimizing our levitator. We hope to really trap some of these disks soon and give some real data on the motional dynamics and the photon recoil. And then we really hope to be able to measure a noise curve soon after that in our interferometer. And that I think will be the interesting thing for that community. Can you really get down to these low strain numbers? And then I just sort of want to close on the fact that if we measured a noise curve and it wasn't very good, it's not the end of the world. So this is some data from LIGO. And then of course, when they switched on LIGO for the first time, their noise curve wasn't very good. And we will probably have a similar evolution where we trap some particles, measure our first noise curve, and there'll be a process of iterative improvement. And the nice thing about these tabletop experiments is they're really becoming quite a lot more popular. So at the same time as we're building our system, there have been a number of other sort of proposals to build these in the lab at the tabletop level. And I think it'd be very cool if a bunch of these turned up in the same part of the frequency spectrum and we could really use them as a global network to sort of localize things more. So in acknowledgement, these are the people who make everything happen in the group. The discs were fabricated by these two lovely gentlemen here. These are the two, Shelby and Aaron are the two PhD students working on this project. I hope they're on the call. And these are our theory collaborators who provided all the graphs you saw earlier. So thank you very much for listening. And I guess I'll take your questions.
Yeah, great talk, George. Thanks a lot. We are perfectly on time, so we have time for questions. I've seen that one already raised his hand. Please go ahead.
It's a very brief question. So what prevents you from going all the way to megahertz or above? Is that thermal fluctuations?
So really what happens there is that, hang on, let me skip through my slides a bit. The mechanical resonance of these particles is basically set by a couple of things. It's set by the, oh, that's annoying. Okay, it's set by the optics, and it's set by the refractive index of the particle, right? So as for the refractive index of silicon dioxide, the position of this PSD in the motional spectrum, that basically turns out to be anywhere between kind of 10 kilohertz and 100 kilohertz for the axial motion kind of along the optical lattice. The other degrees of freedom kind of along the X and Y axis, if Z is really your optical lattice, can be sort of up to maybe 300 kilohertz. That's the highest I've personally done in an experiment. If you wanted to go to megahertz, you would be looking at kind of the vibrational or librational degrees of freedom of the particle, right? So if I trap something that's like a grain of rice or a nanorod and it rotates rapidly, those numbers tend to go up to kind of the megahertz and gigahertz part of the spectrum. I mean, Lucas Novotny's group really did gigahertz like fairly recently in a paper. So that's a really good question, and I'm thankful you asked it. We've thought about this problem in the abstract, like could we use this to go to higher frequencies? And then it basically comes down to the coupling of the librational degrees of freedom to the gravitational wave. So the coupling in terms of the linear sort of motion is very clear from the GR, right? Like, this proper length is not the same as this proper length change. And the coupling is kind of less clear in the case of a tilting particle. That's what it comes down to. Thank you for asking.
Yeah. Mike, you want to add?
Yeah. So the recoil, can you reduce that by using some sort of back action evasion? Is that possible?
Right. Yeah. Again, that's a good question. So that's kind of how I mentioned a couple of papers cooling these objects to ground state earlier, and dynamical back action is kind of a good description of what Marcus Espenmeyer's group did to cool their thing down to ground state. The question with getting rid of the photon recoil in such a manner, and Andy, please jump in if you think I'm saying something wrong here, is very much that when you cool one of these Lorentzian peaks, you tend to squish it a bit and you tend to ruin your Q factor.
Yeah, so that'll be cold damping, which is the Q factor goes down, Q on T remains constant. That's like a normal resonant bar has that property. But so where you damp it and reduce the temperature and reduce the Q, but the signal to noise remains the same. But back action evasion is the readout. You like in a resonant bar, you had all these strobing techniques that you could use so you would measure one quadrature in place of the other, and you could do that classically, or if you're quantum limited, the quantum non-demolition experiment. So these have been well developed for resonant bar detectors. So I was just wondering if that recoil can be reduced in a similar way, if that's like a back action term. That's all.
So maybe I could take a quick stab at that since George asked. So basically the noise here is not necessarily part of the readout scheme. This is just of the trap itself. So I think in this case, we're not limited by the measurement of the motion necessarily, but this is just an artifact of the confining potential being composed of discrete photons. So it's not obvious, I guess. It's a good question, but it's not obvious to me how we would evade that using some kind of a back action evasion.
I mean, in terms of stroboscopics, I mean, some of the people in the levitated optomechanics community do these post operations. I guess that's kind of similar to what you're proposing.
Yeah, no, that was proposed a long time ago by Brzezinski.
Okay, thank you.
Yeah, thanks for the question. That was good.
Is Valerie now?
Yeah, just a quick, simple question. So you showed in your sketch that you have two orthogonal arms. So is that so as you can kind of resolve the tensor structure of the gravitational waves, or what is the motivation for that?
I mean, obviously, there's the motivation of directionality.
Well, let me ask it the other way around. Can you resolve the tensor structure, right? So can you kind of say distinguish, like kind of now kind of, PTA is making a big deal about measuring the Helling-Downs curve so that they're actually sure that they're measuring gravitational waves and not some other force, right? That could be in the experiment. Can you do something similar because you have the orthogonal arms?
I'm sorry, I can't show the slides anymore. My browser just crashed. I'm not sure I'm completely well qualified to answer the question. That may be better suited for one of the theorists in the collaboration. I think Nancy could probably give you a better answer. I can
also ask the question on Mattermost and we can discuss there. Then.
Okay.
Yeah, this is probably a good question for the discussion session today later. Aldo, last question.
Just a quick question. How do you read out the position of these micro particles or micro disks? So this is not clear to me. You read out through the dartboard or in a different way?
So the what we've got set up in the lab at the moment for our other sort of trap particles, and what people who get the really good numbers in terms of picometer displacement sensitivity tend to do in this field, is they tend to use homodyne or heterodyne kind of interference of the scattered fields of the particle. Right, so the light that's scattered off the particle, if you do like a power balanced homodyne detection with your input light, then that gives you very good sensitivity. And then for the ground state experiments, what they actually did was they did sideband thermometry with a heterodyne interference. In terms of how that fits in terms of the interferometer, I mean, you made your question about the dartboard readout. That is a little bit less clear, and that is something we're still sort of actively working on. So what we're doing at the moment is we're trying to build our optical board to be as flexible as possible in terms of enabling us to sort of read out different combinations of things that come through the two cavities, and being able to monitor the two particles sort of outside of the context of their cavity. So I guess what I'm trying to say by that answer is that when these objects have been used in other experiments, they're very much in sort of cavity-less optomechanics. I guess that's mostly true. And taking that sort of readout scheme and moving it to the double armed interferometer is something that we're still working on. Thanks for the question.
Okay, thank you.
Okay, excellent. So let's just keep in mind that we can continue the discussions on Mattermost, and then there will be a discussion session on tabletop experiments today later. Let's thank again George for this very nice presentation. So I stop this recording here.